NASA and GE Aerospace say a modified Saab 340B climbed above 30,000 feet with a megawatt-class hybrid propulsion system. But it was not a giant battery airplane. It still burned jet fuel, and that is why this test matters. The same test aircraft later crossed the Atlantic. GE built the system through NASA's Electrified Powertrain Flight Demonstration, with flight support from Beta Technologies and Boeing. The Saab is a regional turboprop that normally carries several dozen passengers. On one side, engineers installed a flying laboratory, a gas turbine engine, electric motor generators, batteries, high-voltage power electronics, cooling hardware, a gearbox, and a propeller, all working as one propulsion system. Think of a hybrid car, but remove the easy parts.
A car can carry heavy batteries close to the ground. An aircraft has to lift every kilogram. A car can pull over when something overheats.
An aircraft at 30,000 feet needs the power system to keep working in thin, cold air, where cooling behaves differently, and high voltage is more likely to jump through the air. That altitude is the real milestone. Engineers had already run integrated systems in NASA's altitude chamber, including conditions that simulated 45,000 feet. A chamber can reproduce pressure and temperature. It cannot reproduce every vibration, control response, propeller load, weather change, and failure decision of a real airplane moving through the sky. In flight, the turbine and the electric system can share jobs. The turbine still provides dependable energy from fuel. The electric machines can add power to the propeller when the aircraft needs it, or generate electricity back into the battery when conditions allow. GE says the electric powertrain both helped drive the propeller and generated power during the test campaign.
That does not mean the aircraft quietly switched between gasoline and battery mode like a commuter car. The interesting part is power management. Takeoff and climb demand a lot of power for a limited time. Cruise demands less, but it lasts much longer. If an electric system can help during the peaks, engineers may be able to operate the turbine closer to its efficient range instead of sizing every component for the worst minute of the flight. The demonstrator used a megawatt-class multi-kilovolt electrical system. 1 megawatt is 1 million watts. Moving that much electricity through an airplane creates a brutal trade. Thicker conductors reduce electrical losses, but add weight. Higher voltage can reduce current and cable mass, but makes insulation and arcing harder. Stronger cooling can protect components, but also adds pumps, ducts, fluid, and drag. The modified nacelle was even installed upside down to provide extra ventilation. That detail tells you what this aircraft really is. It is not a showroom prototype. It is a test bed designed to expose difficult parts while engineers can still measure and change them. That distinction matters when you hear about the aircraft crossing the Atlantic. The test aircraft later flew across the Atlantic to appear at Farnborough. But the public program reports do not establish that the hybrid system ran continuously for that entire ferry flight. The crossing proves mobility, not continuous hybrid endurance. The stronger released results are narrower. The team reported flight above 30,000 feet and a longest single hybrid operation period exceeding 2 hours. Those are NASA and program partner reports, not independent airline service data. They still do not prove a profitable passenger product. Airlines need published numbers for full installed weight, fuel saved over a representative route, battery life, maintenance burden, dispatch reliability, and safe behavior when an electrical component fails. That is different from replacing both engines on a large single aisle jet with batteries. Today's batteries store far less usable energy per kilogram than jet fuel. Hybrid propulsion works around that problem by keeping the fuel and using electricity where it offers leverage.
So the honest headline is not that electric airliners have arrived. It is that a commercial-scale hybrid powertrain has finally operated where airliners actually fly. The next question is measurable. On the same route, with the same payload and safety reserves, how much fuel does the complete system save after the weight and cooling penalties are counted? If that answer is strong, the first meaningful electric shift in commercial aviation may not look futuristic at all. It may look like an ordinary regional airplane whose turbine quietly gets help exactly when it needs it.